Yes?
Bon.
Session, and we are going to start. We're very happy to have Jose Luis Romero from Vienna. He's going to tell us about sampling, interpolation, and repulsive point processes. So, all things that we love.
Okay, so hi everyone. Thanks a lot to the organizer for putting the workshop together, and I'm learning a lot, and I hope there is a third edition of the workshop. So I'm going to talk about two topics and try to stress the particular relation. So sampling and interpolation, and then its relation to repulsive point processes. So let me start with sampling and interpolation. I'm going to talk about sampling in the sense of functional analysis.
Session, and we are going to start. We're very happy to have Jose Luis Romero from Vienna. He's going to tell us about sampling, interpolation, and repulsive point processes.
So let me start with a simple calculation.
Okay, so hi everyone.
The classical
thanks a lot to the organizer for putting the workshop together, and I'm learning a lot, and I hope there is a third edition of the workshop. So I'm going to talk about two topics and try to stress the particular relation.
Fourier transform is supported on the unit interval, so we expand the interpolation Fourier series, and then we know that the Fourier coefficient of the Fourier transform of the function is the value. So let me start with we compute the inverse Fourier transform. And we get. I'm going to talk about sampling in the sense of functional analysis and the function space.
And we are going to start. We're very happy to have Jose Luis Romero from Vienna. He's going to tell us about sampling, interpolation, and repulsive point processes.
A bit more. So let me start with the calculation, with a simple calculation.
Okay. So hi everyone.
The classical.
Thanks a lot to the organizer for putting the workshop together, and I'm learning a lot, and I hope there is a third edition of the workshop. So I'm going to talk about
the validity of a norm equivalence between one of these pi linear functions or band limited functions and its values on a grid. Now alpha times the integers is exactly characterized by the spacing between consecutive samples. That spacing should not exceed 1, so that this norm equivalence holds. And in practice, this norm equivalence means that there is a formula like this one, expressing the function as linear combinations of the function values weighted with some special functions. And there is a companion statement. There is the so-called interpolation property. We wonder when is it that we can prescribe the values of a function in this space, and with the sole requirement that they are square summable, which is necessary by the first part. And the answer to that is that the spacing between consecutive grid points needs to be at least 1. And well, this is in signal processing is called the Shannon sampling theorem. But it's of course mathematically straightforward, so there are many other names associated to this. And Shannon made it the first step in his theory of information. So one interpretation of this theorem is that the bandwidth of a function, that is the diameter of the support of the Fourier transform, is a precise measure of the amount of variability that there is in this class of functions, because it gives the precise rate at which it needs to be sampled. There is a more sophisticated version of the sampling and interpolation theorem. These are called the density theorems for band limited functions. So here the main reference is Berling, and now we try to evaluate functions at a rather arbitrary set, lambda. And for technical reasons, let's say that there is a minimal separation between different points in lambda, but it's a rather arbitrary set. And the questions are the same. When is it that there is a norm equivalence between the function and the values in a grid? And this question is almost exactly answered by a certain geometric property of the set called the lower density. If the lower density is above 1, there is a sampling inequality, and if there is a sampling inequality, then the density is at least 1. And similarly, the question of interpolation, when is it that we can almost freely prescribe the values of one of these functions on the set lambda with the only requirement that the data be square summable, is almost exactly answered by another geometric property of the set, namely the upper density. Upper density below 1, interpolation, density at most 1. And the limit case is a bit trickier, so that's not so simple to describe. But up to that caveat, there is a quite precise characterization of these properties. The precise notion of density that makes this statement true is the so-called Berling density. So we count the number of points that lambda has on any interval of length r. We normalize by r, and then we either take infimum over supremum over all intervals of the same length, and then we let the length go to infinity. So this is a large-scale notion of density. And the one thing to notice about this large-scale density is that, well, it allows for compensations, right? So the value can be achieved by compensations between clusters and gaps. It's only like at a very large scale that a certain uniformity should be seen. And it's also validation to the meaning of bandwidth, which is the measure of the support of the Fourier transform of these functions. Mathematically, the key object is the zero set of one of these functions. So for example, here, if you want to sample a function, your worst enemy is the zero set of a non-zero function, because here you will get 0 and non-zero. And if you want to interpolate a function, well, you may want to have it be 1 at one point and 0 at the other point. So it's really the zero sets that are behind the scenes. And the main mathematical truth here is that these band-limited functions are entire functions. So if you take one of these functions, consider the Fourier inversion formula and just plug a complex variable, well, that gives an entire function, and moreover with a very precise growth on the imaginary part. So this is what allows one to understand the zero set. And this is behind the proofs. So once this is understood, there are other variants of this theorem. So let me mention a couple of those. Other contexts where this principle applies. So let's change the context to the so-called Barman-Fock space. So these are functions on the complex plane which are square integrable with respect to a Gaussian weight. So this space showed up yesterday under the name of lowest Landau level. And this pi here was a meaningful constant, so the intensity of a field. And in the analogy to the previous space, this is a certain notion of bandwidth, the particular constant here that here is fixed to pi. And there are sampling and interpolation theorems that are completely analogous to the ones we had before. So this is a result from Seip and Wallstein. In this case, the sampling and interpolation properties with respect to L2 spaces weighted with the Gaussian weight are completely characterized by 2D analogs of the densities we introduced before. The Berling density defined in the same way, but now taking average with respect to disks instead of intervals. So the theorem looks quite the same. And well, there is another famous setting where this kind of results exist. The unit disk. So here we consider analytic functions on the unit disk, which with a certain control growth towards the boundary with a polynomial weight. So the power of that weight plays the role of a bandwidth, controls somehow the amount of variability. And there are sampling and interpolation theorems that are quite analog to the ones before. So the possibility of sampling and interpolating this time with respect to this kind of weights, polynomial weights on the distance to the boundary, is exactly characterized by certain densities, which maybe look a bit intimidating, but they are hyperbolic analogs of the ones we saw before. They are doing something very similar, but with respect to hyperbolic notions. So there is quite a parallelism between all these results. And another one I want to mention, with some colleagues, we added another theorem to this list. So the context here are so-called shift invariant spaces. So here we take a function on the real line, say smooth and with some decay, and we consider all possible linear combinations of the integer shifts of that function. So that's some sort of spline-like space. And morally, these are very similar to band-limited functions. They should have somehow 1 degree of freedom per unit space, which is the density of the translation nodes. So actually, if you let G be that special function in the Shannon sampling theorem, so sine of pi x over pi x, you get the pi Leviner space as a consequence of the Shannon expansion I started with. And the reason this is interesting is that if G is allowed to decay fast, well, there is a more local relation between the function and the coefficients. There are truncation errors. So this is why you would consider a better G. And morally, the intuition is that the bandwidth of this space is 1, although functions are not band limited. And well, this is something we proved with my colleagues Karl-Heinz Gröchenig and Joachim Stöckler for a particular choice of G, which is a function whose Fourier transform is a Gaussian divided by a polynomial with only imaginary zeros. So, for example, a Gaussian. There is a sampling theorem like the one for band-limited functions. So, lower density above 1 implies there is a sampling inequality, and if there is a sampling inequality, density at least 1. And there is also an interpolation statement that we prove only for p equals 1. So density below 1 gives the sufficient condition for interpolation. So the theorem looks quite similar to the one for band-limited functions. Technically, there are certain differences. So let me just mention a bit where these functions come up. So these functions G that can be described in this way, so Fourier transform a Gaussian divided by a polynomial with only imaginary zeros, are called totally positive functions, or actually totally positive functions of Gaussian type. And they were studied intensively by Schoenberg. They decay exponentially, so they have this favorable locality with respect to this relation here, and they are quite concrete objects. So here you see one of them, right? So with the factorization of the, and well, these are well known in approximation theory, and so here one can indeed validate the intuition that this space has a modal bandwidth of 1. And let me mention something about the mathematics. So if you recall what I said about band-limited functions, a band-limited function admits an extension to an entire function on the full complex plane with a precise growth on the imaginary part. So that means that one can afford to do the following. If I want to study, say, the density of the zero set, one can consider the number of zeros inside a certain interval, put that interval inside a complex disk, consider the number of complex zeros in that complex disk, and because of this growth, the expected relation is that this number is, roughly speaking, like the diameter of the complex disk. which is the length of the original interval. So that means that one can afford to count complex zeros and still get a good information on the number of real zeros. That's what's behind the proofs of the sampling theorems of unlimited functions. And what happens with totally positive functions of Gaussian type or functions in this shift invariant space is that even though they admit entire extensions, these can have quadratic exponential growth. And that means, from the point of view of complex variable, that the expected number of zeros that you may see inside the disk could be as large as the area of the disk. So that's somehow a bad bound if you want to use that as a bound for the number of real zeros on a real interval. So there is a more subtle relation between real zero sets and complex zero sets. But besides that technical difference, the theorem looks quite similar. So there are a couple more precise characterizations of sampling and interpolation, but not so many. So this is a problem one can pose in great generality, but complete or almost complete solutions are more limited. So let me historically mention another context where sampling and interpolation was studied. This is the so-called problem of disconnected spectra. So now we consider functions with Fourier transforms supported on a rather general set instead of the unit interval, say omega. And to be fair, we let omega have measure 1. And we want to understand the extent to which still what we know for the unit interval applies to a rather general set. Well, and so concretely we ask the same question, sampling and interpolation. When is it that the energy of a function is retained by the samples, and when is it that we can freely prescribe the values of one of these functions on a set? And well, I think this was mainly a theoretical problem when people started studying this, but it became relevant in telecommunications because of something known as multiband spectra. So in certain situations, one owns the right to transmit on certain frequency ranges which may not adapt to a full interval. So in the 60s, many people were interested in understanding the capacity of such a transmission channel. So concretely, it's very easy by comparing this set omega with a large and small interval to prove a so-called soft theorem. So if the density of the samples is large enough, there is a sampling inequality, and if there is a sampling inequality, the density is at least some other unspecified constant. But the interesting question is when these two are close together. So one famous problem from Berlin is whether the necessity of this morally optimal density conditions hold. So for example, whether if we have a sampling inequality on functions with Fourier transforms supported on omega and omega rather unknown but with measure 1, whether that implies that the density of the samples is at least 1, and conversely something similar for interpolation. So this was a problem some time ago, and this problem was solved by Landau. So the theorem is precisely that. Is if within the space of functions with Fourier transform supported on omega with omega measure 1, if there is a sampling inequality, then the density of the samples is at least 1. And if there is an interpolation property, the density of the samples is at most 1. So let me tell you a bit about the main technique here. Consider, for example, the problem of giving necessary conditions to sample one of these functions. So suppose we know that this relation holds, and somehow we want to argue that samples have a certain universal density. So the task is to compare these two, the number of points inside an interval to the length of the interval. So what Landau found is a pivot point here, something to put in the middle to compare these two. And this something is the eigenvalue counting function of a certain operator. It's a Toeplitz operator. So the number of eigenvalues of a certain operators above a certain properly chosen threshold. And that operator it's sometimes called concentration operator. So we consider a function if this space of with Fourier transform supported on omega, we cut it very sharply with the indicator of an interval, but then we project back into the space. So when we cut it roughly, we killed, of course, analyticity, but then we project it orthogonally back into the space. And it turns out that this operator is compact, and moreover, the asymptotic profile of the spectrum can be analyzed, and it looks like this. There is a rather sharp transition from almost 1 to almost 0, and the transition point is the length of this interval. So somehow the amount of degrees of freedom per unit area in this space is provided by this picture. And Landau managed to turn this into a formal argument. So the technique that Landau developed to solve this problem can be applied in a great number of settings. It's a very general principle that applies to many other function classes. So concretely, in very general spaces, one can prove that in order to have a sampling inequality, the density of the samples need to be at least something, and that follows from some abstract version of this argument. And the other question one may have is, well, what about sufficient conditions? So do I know if I have a certain density of the samples, do I know that I have a sampling inequality? Well, and that's a very hard question. In general, there is no converse to this theorem. It's easy to show that the converse implication does not hold, even if we allow for strict inequalities here. But one interesting question is whether one can produce examples matching or almost matching the benchmark here. So that's something that has been investigated by many people, but I want to just mention one well-known example of a way to produce high-quality sampling or interpolation sets. And these are so-called quasi-crystals. So this is a theorem from Matai and Meyer. In the context of Landau, if the sampling set is a so-called simple quasi-crystal, then a converse or almost converse inequality holds. If the density of the samples is above 1, then there is a sampling inequality. And if the upper density is below 1, then there is an interpolation property. And there are other theorems of this kind due to other people. This is maybe one of the best known. So I'm not going to exactly tell you what the quasi-crystal is, but I'll give you an example. So consider these sets. Suppose we take the set of integers and an irrational number alpha, and then to the integer k, we add the fractional part of alpha times k. So we say like a tiny perturbation of the integers. And that tiny perturbation puts the set in some sort of generic position. And well, this one has density 1. But if you scale it a bit up or down, that's a quasi-crystal with density either above 1 or below 1. And that set provides sampling and interpolation properties. And note that this is independent of the particular omega. So without knowing what omega is, there is this generic construction that produces the general construction of these sets is, roughly speaking, you take a lattice in R2, a lattice in R2 in general position, you restrict the second variable to an interval, and then you project into the first variable. And this produces a set of this kind. And as I said, there are other ways many other ways to produce examples meeting Landau's benchmark. So what I want to refer to in this talk is another way to produce high quality examples of sampling or interpolation sets. So this is the second part, the repulsive point processes. So what I'm going to try to argue is that in certain cases, if I let the set lambda be produced by a repulsive point process with enough repulsion, then we get sampling and interpolation inequalities, which in my opinion it is interesting in itself, but it's also a means to study the point process because of this density theorem that means that sampling and interpolation properties require a certain geometric uniformity. So this is what I'm going to talk about. And please feel free to ask questions on any time. So now I'm going to change a bit topics and hopefully then come back to sampling and interpolation. So I'm going to, I think, mention one example specifically. So this is the one from this morning, or a specific case of the one from this morning, the planar Coulomb gas in a more particular setting, I think. So now we consider a random configuration of points on the complex plane. So dimension 2, this is important. And we draw them from this probability distribution. The probability of the density of m points is proportional to this expression here. And this expression has a couple of important parameters. One is a number beta, and the other one is the potential Q. And as it was explained this morning, the potential Q, a typical choice is mod C square, and the effect of the potential is to confine the points to a bounded region, and the other part is doesn't like the points to cluster too much. So there is a competition and something comes out of this, but I'm going to sample randomly from this, as opposed to what we saw this morning where one was optimizing this quantity, right? So this has several names, but let's call it planar Coulomb gas. So the two ingredients are the potential Q, a typical choice is mod C square, and this number beta, whose interpretation is that of an inverse temperature. So when beta is small, so temperature is high, one expects to see more disorder, and when beta is large, so the temperature is low, one expects to see more order. So what do I mean with large and small? One could consider a regime where beta moves with n at a certain rate. So that would be a low temperature or high temperature, low temperature regime. And there is an interesting limit case where we let beta be formally infinity for all n. So that means that we, instead of sampling randomly, we minimize the thing in blue. And that's what it was discussed in the morning, the so-called Fekete sets or minimizers of that stuff. So one of the things I want to refer to is the extent to which some of the things that are known when beta is formal infinity for all n are still true when beta is large or grows with m but not infinity. So that's what we could call a low temperature regime. So a so-called freezing phenomenon. So some pictures, I think you've seen more pictures. So here the standard potential, and I think this everyone has seen many times. And this is the special beta 1, which makes maybe in the morning the conventions were not the same, but this is the one that makes the process determinantal. And with large beta, you see like a more rigid thing, right? So in this morning, we were zooming here and expecting to see a lattice. And, okay. And so let me remind you very superficially the general facts of this. So the points concentrate on a compact set called the droplet under, let's say, mild assumptions. And the density within the droplet, the so-called equilibrium measure, is the Laplacian of the potential. So here, for example, Laplacian constant, and here the Laplacian has a 0 at the center. And one theorem expressing that is this one. For every continuous bounded function, if we compute the average of the function on the sets, the expectation of that goes to the integral of the function with respect to the equilibrium measure on the droplet under mild assumption. So these, I think, the original proofs are for fixed beta here, but this is also true if beta is bounded below. So unless the temperature goes to infinity, as long as the temperature is bounded above, this holds. So this is a very rough description. You can think of many processes that satisfy. This is a totally macroscopic description. And well, the microscopic problem involves taking an average at scale 1 over square root of n instead of everywhere, which is somehow the morally optimal scale for endpoints on the plane on the bounded set. So the freezing regime is a regime where beta goes to infinity with n, and one question is what happens with the microscopic statistics in this regime. So another picture here is the sample with beta 1 and with large beta. So you see that the process is much better organized. So if you take a tiny average here, you expect to see already some predictable number, and that's not the case here. So somehow that's the question. Okay, so let me tell you what we proved with my colleague Yasin Amer. So there are some technical assumptions on the potential. Maybe I think I will not mention everything, but let me tell you the important ones. We assume real analyticity of the potential, and the strict subharmonicity near the boundary for this. Okay, and the smooth boundary, finitely many connected components, so some geometric assumptions, and this is the important one. The beta grows with n at least like log n. It can be much more, it could be infinity for every n, right? But there is a mild growth of the inverse temperature. And so then almost surely the minimal distance between different points with this square root of n scaling is bounded below eventually by a deterministic constant, so a constant that depends on the potential here. So that somehow is a first step validating the idea that this is more rigid. So let me mention right away, I cannot be possibly fair to the many people that work on this, right? But let me mention some things. So there is quite a literature on the case where beta is infinity for every n, where there is no randomness, where we minimize. And we heard about that in the morning. And then for finite beta, my colleague proved a local version of this, where one computes the distance around the given point. So we know that there is a point, and I want to compute the distance to the next one, so a local version of this. And there is this paper that was mentioned in the morning, Armstrong-Serfati, well, up to some technicalities, so maybe not everything fixed together, but essentially it follows from that this should hold in the bulk, meaning that if one discards all particles that are close to the boundary. Then these holes with a number here that is not a constant. It depends in an unspecified way on the distance to the boundary. So this was proved, this came out a bit before ours, and then what we are adding to that is that the separation is global. So it doesn't deteriorate when you go to the boundary. But I'm just trying to emphasize the technique. So the techniques are very different. So I'm just trying to make the point on the how. And the other, now that we know that, let's go back to the picture, that so if I take a tiny microscopic disk of a certain constant, in the microscopic scale we see 1 point at most. So I want to take now a large one, and we know that we see a bounded number of points, and I want to know how many. So we do this. We select the so-called zooming point, Pn, and we build something very similar to those Berlin densities that we use for sampling. So we count the number of random points inside the disk of center Pn and radius L, but at the microscopic scale, so L over square root of n. And we normalize by the microscopic area of the disk. So we count the number of points on a large microscopic disk. And then we send the number of points to infinity, with beta moving, the inverse temperature moving at a certain rate with respect to the number of particles. And then we let the radius of the observation disk go to infinity, right? So by the discussion before, we know that eventually this ratio here is bounded by the separation. But now we want a finer description where we compute an average with a large microscopic radius. So clearly there are two regimes, right? If we are inside inside the droplet in the bulk or at the boundary. So there we expect to see two different things. And well, that's the result. Again, with some assumptions on the potential, the important one being strict subharmonicity everywhere on a neighborhood of the droplet. If the inverse temperatures grow logarithmically, at least logarithmically with n, so the sport is in allowing the mildest possible growth. So it's a lower bound here. And then the following holds almost surely. Almost surely, for any choice of the zooming points, well, if the zooming points are in so-called bulk regime, which means that this scanning disk is always seeing the bulk, so the center is away from the boundary, so that this scanning disk always fits in the droplet. What we see in the limit density is the equilibrium measure at the limit of the zooming points, if there is such a limit. And in the boundary, meaning that the points are in a microscopic sense are in a neighborhood of the boundary, well, we see half of that. And I remind you, I'm assuming that the boundary is smooth, right? So, because of course, if you had a cusp or anything else, you wouldn't expect to see half the density. So maybe what I should maybe clarify is the meaning of almost surely. This means that excluding a zero probability event, this holds for every possible choice of the zooming points. So one could let Pn track the place where the points cluster, right? So if the sample clusters, I send Pm to inspect. So this Pn is some sort of a technical device to do what we were doing before with the infimum or the supremum overall centers of the disk. It's letting us optimize the scanning region. Well, and again, there is many works by others that I should mention, especially concerning the case of Fekete points where the temperature is formally infinity for all n. And again, there is an interaction with this paper from Armstrong and Sefati. So I think maybe it's a bit difficult to explain the relation, but there is a strong relation in the bulk case with this result that came before ours. I think I cannot explain properly all the particulars, but let's say there is something very close that follows from this in the bulk. And the boundary case seems to be completely new. Okay, so now what I want to get to is how this connects to the first part of the talk. Okay, so the relation between the two things is that the way we prove these densities is by showing that a random sample of the planar Coulomb gas in this low temperature regime solves certain sampling and interpolation problems for weighted polynomials. So we consider these holomorphic polynomials on the plane of degree at most n-1, and then we weight them with properly scaled potential, e to the minus n over 2q, where q is the potential. So when n goes to infinity, these polynomials somehow still live in the droplet, meaning that most of their energy is around the 99% of their L2 norm is near the droplet. So what we prove under this low temperature assumption, so that beta n is bounded below by log n, is that almost surely there is a so-called sampling inequality, meaning that the energy of a weighted polynomial on a random sample properly normalized dominates the energy of the weighted polynomial in a certain neighborhood of the droplet, not on the droplet but on a neighborhood. And there is a condition for that, and the condition is that one brings an epsilon, and the degree of the polynomials is 1 minus epsilon times the number of points. So this epsilon here plays the role of the bandwidth in the previous sampling and interpolation theorems. So there is like a marching between the amount of data and the variability of the signals. And conversely, one can freely prescribe a weighted polynomial of degree 1 plus epsilon n on a random sample of the planar Coulomb gas under that temperature assumption, and there is a quantitative relation between the interpolant that one can produce, or one interpolant that one can produce, and the L2 norm of the data. So epsilon shows explicitly in the margin of this. So this, for one particular n, these inequalities are of course trivial, because polynomials of degree n plus 1 point, but the point is in the quantitative relation. And once we prove this, then some variant of Landau's argument applies to say something about densities. So to be clear here, the constants that you see here are deterministic, depend on the potential. What's random is how much one needs to wait to see the inequalities kicking in. And this builds on several ideas you can apply to Fekete points, so in some of the papers I mentioned before. So at the technical level, one problem is to, oops, I think I can, it works. You need to stay there only, yes. Just get comfortable. Mm-hmm.
C'est ça.
Did you even use the microphone now?
Yeah, I think so, yes. Okay, let's hope for that. So to prove this, what we do is we study random Lagrange polynomial. So the Lagrange polynomial based on the random sample. And once we know this, we do some variant of the Landau argument. So we consider, say, a basic shape, a disk square, and we scale it down and we move it either in the bulk or in the boundary regime. And then we consider this concentration operator. So we cut roughly a weighted polynomial and then project into the space of weighted polynomials. So one can study asymptotically the spectrum of these operators, and this is what does it. Okay, so finally, I would like to briefly mention the analog analysis in dimension 1, which is a bit different. One can do a similar analysis in dimension 1. So this is the probability measure from which we sample. So this, in this case, I'm going to refer only to the classical potential. And one may ask the same questions. So this we did recently with Yasin Amer and with Felipe Marseca. So in this case, we can actually say that this low temperature regime, so beta n growing like log n, is necessary and sufficient for this kind of microscopic equidistribution. So the claim is that this condition in red is necessary and sufficient for the following things to be true. If we compute this density, so number of points in a microscopic disk, which in this case involves L over n instead of square root of n, and we do as before, we take limit as the length of the interval goes to infinity, and sorry, first the number of points go to infinity and then the length of the interval. Well, that almost surely gives back the so-called equilibrium measure, which is this semicircle density. But in the one-dimensional case, this is a bit special because, well, of course, this also holds at the boundary, but at the boundary there is a finer scale. So in the boundary this is 0, but you can analyze this at the finer scale. So the finer scale involves this 2/3 here, which is standard for the boundary. And then if you scale with 2/3, you get somehow the expected number here. And moreover, the limbs are uniform here, the limbs on L, uniform on X. So let me just say the sufficiency of this is the same strategy as before, is by showing X.
Can you estimate the sampling cost?
To some extent, yes. Estimate we can, yes. Some of that is in the paper, yes. There is more than one paper, yes, but we can say something about that, yes.
Sorry, what's sigma of x again?
Yes, sigma is the equilibrium measure. So this slide, maybe I shouldn't have introduced. I didn't talk about it.
Yeah, Nicolas?
Yes, one more, sorry. Suppose I take beta dramatically larger
Than log n.
than log n.
X.
Can one say something about at which scale the statement fails? Because you would expect that the larger beta, I mean, you could take L now going to infinity as well. You see what I mean?
You mean in concrete number? So
Not a concrete number, but so I have beta, so you are looking at small temperature. But now I want to look at large temperature and know at which scale the statement, the uniform distribution of points fails. Because you know there is a physically equivalent length scale that you can compute, which has to do with the temperature, the thermal length scale, and you would expect that the equidistribution fails just on this scale.
So let's see if I understand. So n goes to infinity, but still your beta is a number, a fixed number independent.
Beta goes to infinity. Sorry, beta fails to be larger than log n, but by a large amount. Say it's smaller than some power n to some minus number.
Okay, that's a different.
Then I look at the density in a disk, and instead of taking first limit n to infinity and then limit n to infinity, I do something of the sort of Bogard and Erdős that you mentioned, and I take a length which goes to infinity at the same time as n, and I'm asking at which length does the density, the uniformity fail?
And are you asking for the line or for the plane?
Sorry,
For the line or for the plane? Dimension 1 or 2?
any statement would be very nice.
No, the thing is not that I am. In this case, with this potential, there is so much information available that it's possible that you can answer that. It's quite possible. So I cannot give you an answer, but it's quite possible that it's in the reference dimension.
Excellent. So if no further questions, let's thank the speaker again. The first news is that I'm glad to announce that we are now streaming on YouTube.